And now Maxwell's second equation. Maxwell's second equation is derived from Ampere's circuital law. You all know the Ampere's circuital law, which states that magnetic field intensity around a closed path is equal to the current enclosed by that path. Okay, so this current consists of two currents, conduction current as well as displacement current. Before that we all know, I have already taught you several type of densities. Charge density is known as charge per surface, flux density is known as flux per surface, and electric flux density is known as electric flux per surface. Magnetic flux density is known as magnetic flux per surface. Similar to that, current density J is known as current per surface. So di divided by ds. So now I am in need of, take this as first equation. Now I am in need of I. So what I want to find is di. From that I want to take I and I want to substitute the I here. Okay, so di you want to cross multiply with this j. So di is equal to j dot ds. So you want to take integration on both sides, surface integration, and the differentiation integration get cancelled. I can replace it with what? Yes, j dot ds. This j consists of two densities. One is jc and the another one is jd. jc is conduction current density and jd is displacement current density. Okay, so the value of jc is you can take single integration, otherwise you want to denote in the subscript, then only you can able to identify that it is surface integration. Otherwise single integration you collapse that with the line integration. Okay, one thing you take double integration, otherwise single integration in the subscript of s. Both are equal. Okay, you can also take double integration, otherwise single integration with the subscript of s. Okay, so instead of jc I am going to take sigma e, and instead of jd I am going to consider dou d divided by dou t. It is the value of jd and it is the value of jc. Conduction current density consists of conductivity and displacement current density consists of electric flux density. Okay, dot ds vector. So this is, and in the left hand side what I want to take is I. The value of I is equal to integration of h dot dl. So I can replace this I with yes. So here I am going to write single integration of line integration of magnetic field intensity around a closed path. So only I am here representing what? This circle. Okay, so this is integral form of Maxwell's second equation. This is integral form of Maxwell's second equation for what? As time varying field. Okay, for dynamic field I am teaching you dynamic, otherwise time varying, both are same. Dynamic. For static what you are going to do is, it is very very simple. Simply you want to take what I have already told you. For static field means it does not vary depending upon the time. So what you want to do for static field? In the same equation you want to just take out the time varying field. Here t comes now, so you just neglect this term, and this is the same equation without this parameter. Okay, this is the same equation. There is Maxwell's second equation in integral form for static field. If you want to consider this element, this is equation for dynamic field. See here, it is visible now. Yeah, this equation is integral form of Maxwell's second equation, which is derived from Ampere's circuital law for dynamic field. For static field what you want to do? Yes, you want to simply put 0 here. Okay, this equation is integral form of Maxwell's second equation. Maxwell's second equation for dynamic field. For static field, what will be 0? Dou d divided by dou t will be 0. So equation 3 becomes line integral of h vector dot dl vector is equal to surface integral of, what is this? jc. Yes, jc dot ds. That's all. here the value of this is 0 for static field, because the time element comes here, we want to replace, we want to neglect that for static field. Okay, so this is integral form of Maxwell's second equation derived from ampere circuital law for static field. And the another one what we want to do is, yes, point form or differential form. Yes, point form. Point form means what we want to do, which theorem we want to use. We want to use the Stokes theorem to convert line integral into surface integration. So line integral of this particular vector h vector dot dl vector is equal to surface integration of curl of the same vector. Here h vector means here also we want to use h vector dot ds vector. That's it, very easy. So this is fourth equation. Compare 3 and 4. Left hand side both are equal, so I am going to equate the right hand side. That's all. So right hand side del cross h dot ds is equal to double integration of sigma e, which is jc, plus dou d divided by dou t. Here also you want to use vector symbol. Yes, here also you can take vector dot ds. So both it consists of surface integration. So what you want to do? Yes, neglect that integration. Consider only the inner part. What you will get? Del cross h vector is equal to sigma e vector plus dou d vector divided by dou t. Very simple. So this consists of fully differential elements, dou by dou t, and del, the value of del is also dou by dou t. So it is differential form or point form for what? Dynamic field, because here it consists of time. So this is point form for dynamic field, right? Very simple. So similarly for static field, what would you do? You want to neglect this time, that's all. So for static field, the point form would be for static field. For static field, the point form or differential form would be the point form or differential form is, what you want to do? You want to just neglect the time, because static means it does not vary depending upon the time. So don't consider this element, remaining were same. So del cross h vector is equal to jc. jc is nothing but sigma e. That's all. Thank you.